I'm Mario Bisi. I'm from Aberystwyth University in Wales in the UK, and I'm going to be telling you a little bit about planetary and solar radio occultation and scintillations, with a bit of an emphasis on interplanetary scintillation and heliospheric fader rotation. I've got quite a lot of content. I'm not going to cover it all. It's all in the talks that you've got it there to go home with afterwards. I'm going to be covering about 2/3 of what's in my outline there. So I'm going to start off with a brief introduction on the radio spectrum. I'm going to tell you roughly what occultation is, what it means, and some examples of planetary occultation measurements. I'm going to move on then to the scintillation aspect, where I'm going to concentrate a little bit on interplanetary scintillation and give an introduction to IPS, but I'm going to skip the IPS theory part. That's for you to take home and have a look at. Then I'm going to move on to some interesting science stuff and give you some applications of what IPS can do for heliophysics and for space weather. And then I'm going to give you, finally, if there's time, an introduction to heliospheric fader rotation, and then a summary right at the end. So, the radio spectrum. As everyone knows, you've got the whole electromagnetic spectrum. You've got the high frequencies down here with the low frequencies over here. And this is the end of the radio part, covering all of this aspect here of the electromagnetic spectrum. So there's various different frequency bands. They've been named by astronomers over the years for various different reasons. And most of what I do, at least my experience with them, radio observations, has been somewhere around the regions of the UHF and now more recently down into the VHF. So around about 30 megahertz up to 5 or 6 gigahertz. So first of all, what is occultation? Can anyone tell me what occultation is? Or what they think it is? No? No takers? Yeah. So one of the most typical examples is a full solar eclipse. That's also an occultation. So you can also have it like when a satellite moves behind the moon or moves behind a planet. And also you can do it when you get solar occultation, where you have a spacecraft that moves into the sun and then gets occulted by the sun and moves behind it. So this is just courtesy of a colleague of mine, Dr. Richard Fallows at Astron. And as I go through, there'll be a few different images and various plots that are courtesy of him, so I have to give him a lot of gratitude here. So I'm going to start with planetary occultation measurements. This is quite a bit outside of my normal field. So here's an example of measuring Jupiter's ionosphere through planetary occultation. So you had the Voyager 2 spacecraft. It went behind the planet, and it came out the other side. And you can see that there's a sort of a bendy line of sight back to the Earth. And as the radio waves propagate across the outside of the ionosphere here, the spacecraft is occulted, and you can measure the ionosphere through this occultation, and then the radio waves are picked up back at the Earth. So this is a classical Doppler shift, and it has been used many times with various different spacecraft since Voyager 2 as well. So another thing here is that Io, Jupiter's moon, it's kind of tied to Jupiter in a radio sense. According to the literature, there's a J cross B force which is trying to push Io away, and that tends to propel it out of the Jovian system, but then there's a tying in force because of the gravity that holds it back in place. And in fact, there's a lot of power, there's billions of kilowatts of power that goes into the Jovian ionosphere because of Io. And point of comparison, the only other thing in the solar system that creates that kind of power is a large solar flare. And when the slide will change. Then you can get electron density profiles from Callisto. This is done with the same sort of occultation method using the Galileo spacecraft. So again, there were 5 occultations, so it went behind Callisto 5 times, and out of those 5 times, there were 8 usable observations. You've obviously got 5 going in, 5 going out, so there's 10 in total that you can use, but 8 of them were useful. And there were lots of mini ionospheres detected. And this is thought to be, as the moon rotates around, as it's pushing into the Jovian space environment, when the sunlight hits it, it also gets photoionization, and this is what's thought of causing the mini ionospheres. And then another example of the usefulness of planetary occultation is the detection and measurements of Saturn's ionosphere and atmosphere. Here you can see a profile in height from 60,000 to 70,000 kilometers above the equator of Saturn. And you can see that there's a heck of a lot of electron density variation here over that period. By the way, I've put in a lot of references for each of these so that if you want to go read it more and get more details, you can. And then finally, on the planetary occultation side, Saturn's largest moon, Titan, in this case, instead of it occulting a spacecraft, it occulted a star. It was a giant K-type star, and from that you were then able to learn from the scintillations around the outer edge as the moon occulted the star. You can get the stellar signal, and then you can learn again about refractive index changes that tells you about Titan's atmosphere. But if you want an extensive look at this, Hubbard et al. 1993 covers this very well. And then, of course, you've got not just the outer planets, but the inner planets, and you can do the same sort of thing with Venus, and I believe it's been done with Mars as well. And of course, with the Earth, with the advantage of having GPS satellites, and you've got low Earth orbit satellites, you can do the same sort of thing where you can measure the Earth's atmosphere and infer all sorts of parameters. So basically, the take-home message from this part is that using radio occultation, you can get lots of high vertical resolution through the various atmospheric and ionospheric levels of different planets, moons, and it's been done all the way out to include Uranus and Neptune. So, moving on to the scintillation part, who can tell me what they think scintillation is, or give an example, or try to explain it? Yeah, exactly. Yeah, and there's a slightly different version of this. Twinkle, twinkle, quasi-star, biggest puzzle from afar. So the main reason for this was that it was coined by George Gamow in 1964, and it came about the discovery of the first quasar, which was catalogued as 3C273 in the Virgo cluster. It has a very large, bright optical component. It's the brightest optical quasar in the universe. And in terms of its radio strength, it's 46.4 Janskis at 1400 megahertz. So that's a really pretty good, strong radio source. It's up there with the best of them. For those that don't know what a Jansky is, it's a measure of power which is 10 to the minus 26 watts per hertz per meter squared. It's approximately 2.5 billion light years away, which you might think is a long way, except it's one of the closest quasars. So it's not actually that far away compared to many other quasars. It's born of an active galactic nuclei, probably a supermassive black hole at the center of the galaxy. And it's redshifting away from us at a velocity of about 47,000 kilometers a second. So it's shifting away pretty quickly. So this play on the nursery rhyme words here might have been a bit of a joke around at the time, but it's quite serious because just like you've got twinkling of the stars in the sky because of the Earth's atmosphere, then we get twinkling in the radio because of various things moving across between us and the quasar itself. Right, so you've got the electromagnetic, let's stick with the optical one to start off with. You've got it was actually going to be my next question, but you know. You've got the optical light coming towards you, and depending on the size of the source on the sky, so it's got to be small enough because the angle diameter has to be small enough to be smaller than so that the incident plane wave is smaller than the bits of material that are oscillating in the atmosphere. So stars twinkle in optical light because their angular diameters are small. They're typically of the order of milliarc seconds. So they get the interference of the light passes through the Earth because of the turbulent parcels in the Earth's atmosphere. And the reasons that planets don't scintillate is because they're larger in the sky. So the large angular diameter, by comparison, is several arc seconds. And then this doesn't allow them to scintillate because the plane wave is too large compared to the size of the packets that are sort of transmitting across, your line of sight then. Does that make sense?
So it's an issue of if you've got a wave of light coming for a plane wave of light coming towards you, and if the pixels in that plane wave are
of the right width.
large light width, then you get so much.
Yeah. So yeah, my question was going to be why don't planets scintillate? But yeah. Say that again, sorry.
Whether this phenomena at the observer point is the scattering by diffraction or diffraction pattern.
It is a diffraction pattern, but when I get onto the radio part, what we can consider is the diffraction pattern is just a sum of discrete scattering screens. So that simplifies the analysis. So instead of having a continuous integral along your line of sight, you can use discrete scattering screens where in certain conditions, which I'll explain in a little while, you can actually just treat them as individual scattering screens as your radio wave comes towards you through, in this case, I'm going to explain about the interplanetary medium. So as it comes to the solar wind, and of course, that is going to have relation to space weather. Does that answer what you're asking? Yeah. Okay, so radio astronomy then. So why did they twinkle? So you've got the same principle. You've got these electromagnetic waves, except this time in the radio regime. They're traveling, first of all, through the interstellar medium as they enter the galaxy. Then they enter through the interplanetary medium. And then eventually they come through the Earth's ionosphere where we detect them with the radio telescope on the Earth. So you've got to consider that you've got components in the interstellar medium, you've got components in the interplanetary medium, and then you've got the Earth's ionosphere as well. And anything else is pretty much negligible. We can ignore everything else. So just like as I was saying about the source size for the optical regime, it's got to be a certain size on the sky or smaller for it to twinkle in optical light. Quasars and other similarly compact radio sources also have to be very small. And we're talking about milliarc seconds or less if you want to do interplanetary scintillation, and that's also where a lot of the ionospheric effects come in too. And if you want to do interstellar scintillations, if you want to measure the interstellar medium, you've got to have microarc seconds. So by comparison, if you want to try to think of this, Neil Armstrong, when he was bouncing around on the moon, his big toe, as viewed from the Earth, is approximately the maximum scale size of a microarc second quasar if you want to do interstellar scintillation. We can take account of interstellar scintillation because a lot of our sources are between the microarc second and the milliarc second size, so we don't really get much in terms of interstellar scintillation. But also, interstellar scintillation propagates, the interstellar medium propagates at around 30 kilometers a second, so that's a lot slower than what the solar wind propagates out at. So again, we don't need to worry about it too much there. We just need to worry about the ionosphere and the actual stuff in the solar wind that we're interested in. So I'm going to show you pretty pictures to start off with. Here are some of the radio dishes that we've used the most in Europe anyway. They're the EISCAT radio antennas. They're scattered across northern Scandinavia, including the archipelago of Svalbard. Then you've got the very large dish, the Lovell telescope in Jodrell Bank in the UK near Manchester, and the Mark II, which is actually a concrete dish, not an aluminium or steel dish like many of the others. And then what we've been moving into more recently, as some of you may or may not have heard about, is something called the low frequency array. And this is one of the new next generation software telescopes where they have no moving parts, they have no directional capability in terms of moving the array or moving the telescope, but everything is done in software. So you just turn it on, it has the entire field of view of the sky, and then you make your beams or your imaging all done in software. And here you've got the central core in the Netherlands. And then you've got the UK station here. And just for comparisons, you get a size of what these tiles are. My colleague, Dr. Fallows, is about an inch taller than I am, compared to the size of the tiles and of the dipoles. On average, the stations have between 48 and 96 tiles, or 48 to 96 dipoles, depending on which part of the array you're talking about. These tiles here are the high band array, which goes from 110 megahertz up to around 240 megahertz. And then these dipoles are the low band array, and that goes from around 10 megahertz up to 90 megahertz. And of course, you've got the FM radio band from 90 to 110, where you pretty much can't do much in terms of radio astronomy, certainly not in the Netherlands anyway. So where are these stations located? Well, there are currently 5 online. These are the international stations throughout Germany. There's 5 there. There's one in Paris. Not Paris, sorry. There's one in France. There's one in the UK. There's one in Sweden. And then you've got the core and the cluster of the other stations around the Netherlands. And then the yellow dot there near Hamburg is one that's about to come online sometime later this year. So as I said, it covers from 10 to 240 megahertz with that FM radio band gap in the middle. It's got plenty of collecting area. And what we'd like to do, and I'm going to go on to explain 3D tomography in a little while, is that we try to improve the resolution of the 3D tomography to try to improve our science and the understanding of CMEs in the solar wind, but also with the inference of improving space weather forecasting using this method. I should also note, because I come back to it later, that there's something called the Kilpisjärvi atmospheric imaging receiver, and this is also up in Scandinavia. It's on the tri-border between Finland, Norway, and Sweden, and this is a system that's very much based on LOFAR technology, but configured in just a slightly different way, because they want to use it for atmospheric science primarily, and we want to use it for interplanetary scintillation. Yes, yeah, there's ultra-fast fiber optic cables. I think it's of the order of 10 gigabits a second. Gigabits a second, sorry, yeah. They need that because the data rates are phenomenal. For a simple IPS experiment where we measure just intensity, we have of the order of 1/4 of a gigabytes for 15 to 30 minutes observation. If you were to do full Stokes parameters, and if you wanted complex voltages and row voltages, you're looking at of the order of 1 to 1.5 terabytes for 15 to 30 minutes of data. And that's especially so if you're using all of the international stations and the core. I mean, the more you measure with, the more the data rates go up, and it really is phenomenal the amount of data these systems can take. And just for a point of interest, you've got the Japanese system, which we primarily use for tomography, and you've got the UTI system, which is a giant radio telescope in the Nilgiri Hills in India. So I'm going to skip this part. Oh, no, not actually. I'm going to go through this part and skip the theory part. So what is interplanetary scintillation? You've heard me rabbit on about quasars and about radio waves and all the rest of it. So what we have here is you've got the sun, you've got the solar wind propagating out from the sun, and in the solar wind there's density inhomogeneities. So you've got turbulent structure and density variations in the solar wind, and as that's moving out across your line of sight, you've got the radio waves coming in here from the quasar, and just like your sky twinkles at night because of stars, then the radio waves twinkle because of the scintillation coming out. And what you can do is you can measure the scintillation signal with 2 telescopes simultaneously on the Earth, pointing at the same radio source. And then from those signals, you can cross-correlate them to get a measure of what's going across your line of sight. So in this case, it's going to be predominantly the solar wind. Of course, there's a little bit of ionosphere in there, which we take account of by filtering, and I know that the next talk is going to be based more around ionospheric scintillation. But what we care about is what's going on in the solar wind. Is there a CME in there? Is it a slow stream? Is it a fast stream? Is there something potentially coming towards the Earth? If it's a CME, what can we understand about it? What other data can we then bring in to complement the IPS, or what can IPS complement elsewhere? So there's an example of a set of time series where you've got the 2 different antennas here. The signal comes across, as you can see, there's lots and lots of bumps and wiggles going on. So there really is a lot of fine structure crossing your line of sight. And the other thing which you can get from this is when you take a power spectrum, you can have your arbitrary power, or in this case, it's a scintillation index. And as you go further out from the sun, if you stick to the same frequency, then the scattering reduces in its intensity. And if you go too close to the sun, you pass the point where you enter from weak scattering to strong scattering, and then you get destructive interference, which that also then decreases your ability to record, so that decreases the intensity. So if you take a mean curve of, say, thousands of observations, which is shown here from the UTI radio telescope, that is where you can consider what your ambient, everyday solar wind is at that direction on the sky. So then if you've got something going on, say if you've got a big CME going through there, then you'll have an enhancement on this. So you'll receive a larger amount of power in your scintillation, so the scintillation index will go up. And of course, if you say, for example, got a CIR going through and you've got that rarefaction region behind the CIR where there's not much behind it and the material is sort of swept along, then you'll get this sort of degradation here. And that tells us that then there's a reduction in actual density variation that's going on, and that can be referred to a reduction in density too. So going back to the power spectrum, what can we get from it? Well, we can get, first of all, something called the Fresnel knee. This tells us what the speed of the solar wind is. But of course, you can have more than one stream crossing your line of sight, so sometimes you get more than one Fresnel knee. So it gets a little bit difficult in a sort of interpretation if you're just looking at a power spectrum, and that's when you have to bring in the proper solar wind modeling analysis tools. Then you've got a power law drop-off, and this tells you about the density variation and the density of the solar wind. And from that, you can infer something called a G level, and when I go on to explain the tomography, it's the G level that we use to correlate to get a density at the end of it, so density of the solar wind. Then down here is usually where you get the most mischief from the ionosphere, so we use a high-pass filter to get rid of that. And up here is where you get the most mischief from interference, people's mobile phones, and so on and so forth. So we use a low-pass filter to cut out the background noise and to cut out any other interference that's often caused. Okay, so last slide on Introduction to IPS. So I said you can get a cross-correlation function. So let's concentrate on this one first. So here you have, from Klingel-Smith's thesis back in 1997, an example of a set of observations where they used 3 antennas, and the baselines on the Earth between the antennas were different lengths. So when this gets projected on the sky, you get, again, different lengths as the propagation of the solar wind comes out. So if you've got, for example, here, beam A and beam B, you're looking down from the top of the sun, looking down onto the Earth, you've got your beam. So you're looking as if you're coming from the quasar. Then if you assume that there's roughly a radial outflow, I mean, there's not always a radial outflow, but just for simplicity, we assume there's roughly a radial outflow. So your solar wind is coming out from the sun, and the other radio source looking down onto the antenna. And what you have here is 2 sets of baselines. So you've got your parallel baseline, which is parallel to the solar wind outflow, and you've got your perpendicular baseline, which is perpendicular to solar wind outflow. And what you want to do to get the maximum chance of a good correlation is you want these two to be lined up here as much as possible. And also what it means is that you get a feel for the actual outflow direction. So if you get a very good correlation at, say, a weird angle like this, and as you get towards more of a radial angle, your correlation goes down, it probably means that the solar wind isn't actually flowing radial at that point. It's actually flowing non-radial. So you get a measure of the direction output as well. But what about increasing baseline? So as I said, if you increase the baseline, it changes the cross-correlation function. And what it essentially does is, because you've got a longer time span between first sight and second sight as the solar wind is moving out, it means you've got more chance of picking up more than one solar wind velocity in there. So if you look here at 75-kilometer baseline, you've got a single peak. It's only just coming out on the slide, but there's a single peak in the cross-correlation function. So then if you look at the 150 kilometers, you've got a single peak with a bit of an off thing coming down here. Then you go to 210 kilometers, and you see that there's definitely a second peak coming in there. And what that means is that there's 2 separate streams of solar wind crossing over your line of sight, you can actually detect and measure both sets of solar wind streams. Sorry about that. Right, so IPS with LOFAR. So we've actually made quite a good progress. It's been difficult because, like I said, it's not a traditional radio telescope. There's one paper out describing the experiment already, and there's another paper on the way. But what can we do with it? So let's look first of all with the IPS. And when you have a passage of a CME, there's something called a negative lobe at 0 time lag. So this can be seen here. And what that is caused by is usually a CME crossing over your line of sight. So you've got these density features that are flowing out in the solar wind. And because of the flux rope-like structure of a CME, as that's bashing into the solar wind, at the front of it, the density structures quickly rotated. And because they're slightly rotated, as that crosses over your line of sight, you then start to get an anti-correlation because you're trying to correlate one thing that is sort of horizontally elongated with the front of the CME or the top of the CME where it's more vertically elongated. So this twisting of the density structures then infers that you get a negative lobe at 0 time lag. So that's our traditional signature from a single IPS experiment, a single IPS result. And what we did here is we just used a whole bunch of other data coming from stereo, from the core on board stereo, the LASCO, you've got SDO, you've got a J-map, which basically is a height-time map of a particular point with the heliospheric images, and we've done some 3D MHD modeling, and the upshot of it is that it all ties in nicely with the CME. But the most curious thing is that here, if you look at the ecliptic layouts, you've got the Earth, the Sun. This is the CME propagation direction. There's the IPS P point, so okay, this is good. It's crossing the part of the line of sight that we're most sensitive to. But the CME went mostly below the ecliptic. Yet we have this very, very nicely defined, strong CME signature. So we need to work out now exactly, go back to the drawing board and look exactly how much of an influence small aspects, small grazing incidences of CME have on the effect of the cross-correlation function compared with cutting through different parts of a CME. Traditionally, we've always thought that if you get a nice strong negative lobe like this, that you're cutting through the main front part of the CME and not cutting through the northern flank or the southern flank or east or west flank. But in this case, it really is just cutting through the very, very top edge of the northern flank. Here you can see that there's the ecliptic and the CME is going very much down to the south. So there's a bit more work now for us to go back to the drawing board here. But you might ask, well, how do you know that IPS is working on LOFAR? Well, we've done that already. We went back, we did a simultaneous experiment where we observed the same radio source with EISCAT. So this is a cross-correlation function with EISCAT. There was a lot of noise in the data, so we have a very, very weak cross-correlation function here. And we did it with 3 radio stations from LOFAR with 3 sets of cross-correlation combinations. And if you look carefully, you see that the velocity of the solar wind coming out is 430 kilometers a second in every single one. So that is much reassuring to know that our experiment is working on LOFAR. Now, why would we want to use LOFAR if we can use EISCAT and use other things? Well, LOFAR has the added benefit of a huge frequency range, and you can do, at the moment, up to 80 megahertz in your bandwidth at any one time, which then allows you to do something called a dynamic spectrum. So here, you've got your frequency, you've got your time, and all of these vertical lines that you see, all these bumps and wiggles in the vertical lines with the different colors of intensity is your actual interplanetary scintillation. So you can imagine that originally we just have one time series going through there at one particular frequency with all the bumps and wiggles. Now we have a whole plethora of them covering the entire frequency band of LOFAR just about. In this case, it was done slightly separated, where this observation was taken just after this observation, but we are working on a way of using the entirety of the LOFAR frequency range to be able to do IPS all the way from low frequencies to high frequencies. And then that will get us a better handle on where the turnover point from weak scattering to strong scattering occurs, and where we can reliably use these radio frequencies in the heliosphere to detect CMEs, for ambient solar wind, what radio sources perform better than other radio sources, and so on and so forth. You mean here? Well, the bit I skipped tells you that each radio frequency you look at is sensitive to a different fundamental scale size in the solar wind. So the higher the frequency you go, the smaller the scale size. As you get closer into the sun, if you go to higher and higher frequencies, you get the more dense, finer scale structure, so you can stay within the weak scattering regime by going to higher frequencies. And what you can see here is there's a little bit of a drop-off in signal at the highest frequencies because you're actually coming down. If you remember that curve that I showed, you had the curve that went up and down in the power. So the further out from the sun you go, the lower the power goes. Well, the same thing applies to frequency. If you stick to one point away from the sun, say you're 50 solar radii off the sun, and you've got ambient wind flowing across, there's going to be a particular frequency where you're going to get maximum scintillation, and then frequencies below that are going to drop off quite gradually. So as you can see, there's a gradual decline in the intensity variation here. And then if you go all the way up to this aspect here, you can see that it actually virtually disappears very quickly. And that's where you go into strong scatterings. You've got lots of destructive interference going on, and that actually reduces the scintillation power again. So if, for example, a CME were to smash through here at some point, then we'd expect that this relationship would change a little bit because your density structures would then change as it's crossing over. So you get more turbulence, you get more variation, you get an increase in density. So that will affect where in this entire frequency range your greatest scintillation will occur and how that curve will drop off. So it's almost like you're having a radio source moving out from the sun in a matter of 15 to 30 minutes. Because we can observe over the cross of a large frequency range, that's kind of the same inference there. Does that make sense? Right. Right. Yeah. Yeah. Sorry. Yeah. And then Kyra that I mentioned earlier is up in the high Arctic. And at these frequencies, ionospheric scintillation really is a problem because you've got a lot more going on in the ionosphere up there. And I'm just showing this for illustrative purposes, where you can actually see refraction signatures in the scintillation pattern. So up here, you've got a little bit of IPS, but there's a lot of ionospheric scintillation. Here, you've got ionospheric scintillation dominating, and here, you've got refraction effects. And so we need to really think now how we're going to use low-frequency systems in the high Arctic, because EISCAT has just been transferred over to 224 megahertz. And we're really working hard now to try to figure out how best to do IPS when the ionosphere is actually a major player, much more so than it was at the higher frequencies of 900 to 1400 megahertz in the past. So 3D reconstructions that I alluded to. So you can take your IPS observations, you can take lots of them around the heliosphere, and then each of them goes out and it can map back to a source surface somewhere at some distance from the sun. So say 15 solar radii from the sun. And what you do is when you map these down onto the source surface, you can unravel the solar surface into a counter map. So you've got your solar rotation and you've got your latitude. So this is your longitude, there's your latitude. And then within this particular solar rotation, you've got whole lines of sights or parts of lines of sights mapping back onto the counter map. You can do this day after day after day after day, and eventually you'll get enough data where you can then build up a picture of the inner heliosphere. But so what's the limiting factor? Why can't we do this all the time? Well, observing time is an issue. These LOFAR in particular and EISCAT are not dedicated to IPS. They're actually, LOFAR is dedicated to radio astronomy, and anybody can bid for time for it. And EISCAT is primarily used as an ionospheric instrument for incoherent scatter. So what do? Well, there's an array in Japan that I mentioned that is dedicated to IPS. So that's one system that we use quite a lot. And recently we've been using the UTI telescope, which has between 1,000 and 3,000 lines of sight per day. So here you're looking at the mapping back of around 20 to 40 lines per sight per day. So if you imagine you've got 1,000 to 3,000, then this becomes a lot more dense, and your heliospheric coverage is a lot more in that case. So I'm going to show a few examples of what we've been doing and why it's such a good technique, or at least why I think it's such a good technique. In 2004, there were some very intense geomagnetic storms. There are a whole bunch of CMEs that came towards the Earth. There's a whole lot of confusion over what did what to whom in terms of the Sun-Earth connection. The first geomagnetic storm was hitting the Earth around the 8th of November, probably caused by the CME on the 4th of November. But then there was a second geomagnetic storm straight afterwards on the 10th of November, where there was this intermingling of CMEs going on, and there was a merged magnetic cloud as it hit the Earth. So what we did was we used UTI data in this case. So you have all of these lines of sight around the heliosphere. You build up a picture of the solar wind in terms of velocity and in terms of density. And then you think, well, what can I do to make sure this works? What can I do to ascertain that I'm getting a real picture? So what you can do is you can extract at any particular point in the heliosphere a time series of the velocity and density variations. So what we did was we looked at the position of wind. So this is at the L1 point. It's 100th of the way between the sun and the Earth, between the Earth and the sun. And what we did was we took a measure of the velocity taken from the tomography and compared it with wind, and of the density taken from the tomography and compared it with wind. And you can see, okay, we're slightly enhanced over the actual levels, but we've done a very, very good job in reconstructing a very complex structure at the time. So there was another CME. This one was back in the 2nd of June 2008. It had no real source surface origination, so some people term them stealth CMEs. I just think of them as slow and slowly sort of bubbling out, coming out from the low corona. It started off actually around about the 31st of May or the 1st of June, and it didn't reach coronagraph images till the 2nd of June, and then it didn't reach the Earth till the 6th or 7th of June. So it really was a slow CME. But another thing that we can do with the tomography is when you visualize it in 3D, so you've got the Earth, the Sun, you've got ecliptic north, you've got solar north, you've got the ecliptic plane, and here you've got density structure throughout the inner heliosphere. Here I've removed all of the low density stuff, so you've got things here that are upwards of around about 10 particles per cubic centimeter. And similarly, you can do the same with the velocity structure. But even better, if you've got a CME, you can confine the CME in a set of cubes from which you can work out the volume, you can work out the mass, therefore you can work out the energy, and you can get a feel of the kinematics of the CME coming out. And then what you can do is you can look at other ways of doing mass structure, look at other ways of obtaining masses of CMEs. And what we did was we compared it with masses obtained from the LASCO coronagraph and from the Core 1 and Core 2 coronagraphs. They agreed pretty well in terms of the inner regions, and then the mass started to increase as the CME started to propagate out. And when we measured it around 0.7 AU, it was double the mass from where it was in the Core 2 field of view at around about 20 solar radii. So what does this mean? Well, it was a slowly propagating CME. There was a faster slow wind stream coming behind it, so there's a high likelihood that it was mass loading on the back of the CME from the slow wind that was just pushing it along and ushering it out through the inner heliosphere. And finally, here with very, very few lines of sight, using EISCAT, we have the slow portion of co-rotating regions. Bearing in mind that EISCAT, at best, we make 9 to 12 observations per day. And it was not believed that it would be possible to make the tomography work with so few lines of sight, because you don't have the spatial coverage like you do with STELab, and certainly not like you do with UTI. But here you can see these nicely co-rotating, slow portions of the co-rotating streams coming around. You've got a small CME coming out there, and there's a small CME going out there, and they were verified with heliospheric imaging with the stereo HIs. So this was a nice surprise, and if you carefully watch the rotation actually roughly measures the rotation rate of the sun in the ecliptic. So that was a very nice advent for us. Okay. I think the thing has gone off loud. Yeah, it's not showing what I've got on here. That's why I switched back to the laptop. Oh, there we go. Okay. So, first of all, does anyone know it's on the screen, so never mind. Anyway, Faraday rotation. So, Faraday rotation is you've got your polarized beam of radio emission coming towards you, and as that beam passes through a birefringent medium, so an ionized solar wind plasma, for example, this polarized plane rotates. And from that rotation of the plane, you can infer then that there's some kind of feature going through there that is causing a disturbance. So, for example, a CME would cause not a significant amount of rotation measure, but a fairly significant amount of rotation measure. So this polarized plane would actually rotate. So first of all, how do we know what the polarization should be, first of all? Well, for many years, astronomers have been looking anti-solar directions far away from the sun and measuring pulsars, for example, that are well-known polarized signatures. Those polarized signatures come with an inherent rotation measure, and then from that, you can then work out what else is going on. Well, the next biggest contributor that you have to worry about is the ionosphere, and then the one after that, we hope, is the heliosphere. So if a CME goes through there, we're hoping that it'll be on the order of 10% to 30% of the same kind of scale as what the ionosphere causes. Then we can do is differential rotation measure to obtain what is actually happening because of the heliosphere. And if you then input that into some kind of mathematics or tomography, you can actually, hopefully, deconvolve the three-component magnetic fields. And of course, you can go after BZ, which we think is the biggest cause of the geomagnetic storms because of the solar wind and the CME inputs. So there's been a little work done by other authors on this already. They've looked at trying to calibrate the Faraday rotation by understanding, first of all, the ionospheric contributions and by tech modeling. So here we have the actual set of measurements from a pulsar. These are the blue circles here. Here's the time in UT, and this was sunrise. So this was your crossing into dusk to dawn period. And you can see that there's a bit of a variation, and again, a bit of a variation here, and as expected, as you cross into daytime, the rotation measure increases. So what you can do is you can model what the expected contribution is from the ionosphere. And here is the scale on the right that tells you what the ionospheric contribution is. So you can see that from the interstellar medium, you're looking at quite a significant rotation measure. But from the ionosphere, you're looking at between 5 and 10% of the actual contribution. And in fact, if you subtract out this ionospheric pattern from the interstellar medium, you get what you'd expect, which would be an approximately flat response. So this is somewhere far out from the sun where you're not going to get any heliosphere interfering. you've got a known rotation measure for a known pulsar, and then that's your starting point. So what you can do, in theory, is then start looking closer into the sun, and then once you've taken account of the ionosphere, anything then varying above the standard rotation measure, or indeed below the standard rotation measure, has to come from the heliosphere. So it's thought that the heliosphere, in terms of the ambient solar wind, is going to be about 10% of the ionosphere. So you're probably not going to detect the ambient solar wind. But if a big CME comes through there, it's going to be somewhere, as I said, around 30 to 50% of the equivalent of the ionosphere. So therefore, you're not going to have a flat line. You're going to have a small variation. And hopefully from that, we'll be able to infer eventually the actual magnetic field of CMEs coming out from the sun. So again, going back to the tomography, here we have, looking down from the north of the sun onto the ecliptic plane, you've got the Earth, you've got stereo B, stereo A, the sun in the center. This is in density. This is for a counter-rotation 2121, but there's a CME of interest on the 7th of March 2012. It's not this structure which is already out beyond the Earth. It's this little blob that is coming out towards the Earth there. So why did we look at this period? Well, it's a nice, fairly segmented CME away from most of the things. It looked pretty much isolated in the chronograph images as well. And what we can do is we can do from the ambient magnetic fields just to see how things might look in the heliosphere. So here you're looking from the Earth. The sun is at the center. Then as you're going out from the sun, you've got your 45 degrees elongation angle. You've got your 90 degrees elongation angle, which is looking out 90 degrees from the sun-Earth line. And here you've got the G-level variations. This is the density turbulence variation. And here you've got what is inferred as the rotation measure, but only from photospheric magnetic fields. So this is just your ambient photospheric magnetic fields propagating out with the density. And of course, as you put it in the 3D and propagate it out, the density causes bumps and wiggles in the actual magnetic field. And this is kind of the rotation measure you get from no input of far rotation observations, but just with density and ambient fields. You can see that it's not a nice uniform thing. There's some activity going on here. So that tells us that hopefully, if we're able to do the far rotation observations, then we can actually look at what the rotation measure is on the sky, and then from that we can get three-component magnetic fields. So this was that event earlier in the month that most forecasters missed. There was a slight warning on one of the SWIPSI reports that there might be something little coming along the way, and then there was a big geomagnetic storm. Nobody really realized what was going on until after it hit the Earth, and there was a big DST response. But if you look here again, these are ecliptic cuts looking down from the north. These are density, these are velocity. You can see that there's this sort of co-rotating sort of region here in terms of slow wind coming out towards the Earth. Then a little later, there's sort of this breaking off, and in the meantime, there is some high velocity stuff going through there, and then in between these 2 points, there is almost a CME-like feature that went out between there. So what possibly happened was that a CME sort of broke through into the co-rotating region, and then because of the turbulence and the bumping along of the magnetic field lines, that caused a big BZ, and that's what caused the geomagnetic storm. And as you can see, this is with ACE data and the tomography. Indeed, there was a big density enhancement. Tomography is slightly enhanced over what was seen by ACE, but the velocity pretty well matches up almost 1-for-1. So this is very good in terms of forecasting. So in summary, both planetary and solar occultation experiments provide us the ability to measure and learn about planetary atmospheres, ionospheres, the solar atmosphere, the corona, and then, of course, when you move into scintillation, the solar wind. And, of course, there are whole other things you can learn from as well, like I mentioned about the interstellar scintillation, for example. IPS is pretty much a powerful tool. It was very popular in the 60s and 70s. somewhat through the 80s. Then it sort of lost its flavor a little while. And I think in the last few years, it's really coming back now, especially with so many new IPS systems coming online and IPS-capable systems coming online. Our experiment with LOFAR in developing the IPS experiment is pretty much there now. We're still learning a lot about the radio sources, about which ones are good at these low frequencies, because we're moving out of our comfort zone. You know, we're used to high-frequency IPS. We're moving into low-frequency IPS. But there's a lot of experience to be gained from the old days where you had the Cambridge array in the UK and the UCSD system in Southern California, which operated between 76 and 80 megahertz. So we're not completely into a new realm. We're just going back to having to look at how things were done in the past. There's planning now underway for an experiment to try to go after the heliospheric fired rotation. And of course, there's Briny Jackson and his group there are planning to try to prepare the tomography for fired rotation input. So if and when the time comes that we can actually give him some data, then he can stick it in his tomography and hopefully get BZ out of it at the end. I mean, that's kind of the holy grail almost for space weather forecasting at the moment when it comes to CMEs at least. So go back and have a look at the basics of the IPS theory. There's plenty of papers referenced throughout, so if you want more information, of course, you can always email me at any time. And basically, you know, scintillation's good, planetary occultation's good. It all helps for the heliophysics system, but then there are lots of complications with, you know, your radio sources, with the ionosphere, and so on and so forth. And I just want to leave you with one last thing. This was the EISCAT and Merlin set of joint observations, simultaneous between northern Scandinavia and the UK. And you've got baseline here of around 2,000 kilometers. So we thought, well, there's no way in 2,000 kilometers is a solar wind microstructure going to remain coherent. But it did. We have two very discrete solar wind streams. You've got your first solar wind stream here with a velocity which I think, if I remember right, was around about 550 kilometers a second. And then all the way down here at 8 seconds time lag. So this is your partial solar wind passes your first line of sight. It's traveling out. And 8 seconds later, it passes your second line of sight. And there's still correlated features. There's still features that maintain constant in the solar wind on the scale sizes of around 150 kilometers that then give you the second peak, which was just around about 250 kilometers a second here. So that was just about what the solar wind was doing at ACE at the time. It was around about 280 as measured by ACE. So that was a very nice surprise for us that these little density turbulence features remain coherent for so long out in the solar wind. And that's everything. Thank you. I don't know of any applications to it, but I know that basically it messes around with us if that happens. Any thunderstorms around the time of it trying to take IPS, especially with LOFAR, because the way LOFAR works is you get the radio waves coming in from all over the sky. You get this interference going on, and it messes around with the experiment quite a bit. But as for using this kind of experiment to detect sprites, or detect this atmospheric thing going on, I don't know if you could. I don't know of any time that it's been used, and I'm not sure that you could use it. I'd have to think about that. Well, for IPS to work, or for scintillation in this sense to work, you need things to flow across your line of sight. So if you don't have the atmosphere flowing across your line of sight in the ionospheric part, in the actual charged particles part in the plasma, then you're not going to get any scintillation pattern, because that's what causes the scintillation pattern, is the small scale features crossing the line of sight. because at 327 megahertz with that particular radio source, that is where maximum correlation occurs. In the mathematics, it shows where the crossover point of weak scattering to strong scattering occurs. So at different frequencies with the same radio source, you'll have different distances from the sun. So for example, if it were 1400 megahertz, then it would probably be closer to 30 solar radii. But if it's 100 megahertz, then it'd be closer to 80 solar radii. And it's just down to the scale sizes at those distances from the sun relative to the actual frequency of the radio waves coming in from the radio source. So if they don't match up right, just like planets don't scintillate in the sky because of the frequency width, the width of the source doesn't match up with the size of the homogeneities in the Earth's atmosphere, then the width of the source at that particular frequency and the wavelength of frequency isn't going to match up at different distances from the sun. So your scintillation goes down, or worse, if you go too close to the sun, it goes down because of destructive interference. But at that point, though, if it gets too high, then the assumption of each scattering screen being an individual case of scattering breaks down because it all gets complicated. So instead of it going one scattering screen, okay, I'll scatter here, right, I'll scatter here, I'll scatter here, I'll scatter here, it goes, right, I'll scatter here, 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 and here, and here, here, and here, and here. But you got to here, you don't know, you can't, you know, it's not actually added up in a linear sense anymore because you've got constructive and destructive interference taking place. So overall, the amount of scintillation decreases if you go too close into the sun because there really is just too much going on. So you no longer have the assumption of discrete scattering screens as it's propagating towards you, as the radio waves are propagating towards you.
At the observer's screen, at the point observer and the Earth, it is the interference pattern or it is the diffraction pattern?
It's sort of both. It's sort of a diffraction pattern, but you can build it up from a set of discrete scattering points. So it is sort of both in that sense, yeah. What she's asking is, during 3D tomography, is there assumption that everything is static during the observations? No, because if it were static, then we wouldn't get the actual structure out. It's time-dependent tomography, which means that everything is flowing out. So each individual observation is locked to a particular point on the sky in time. And what you do is you map everything back onto that source surface. You have a kinematic model of conserving mass and mass flux. That propagates out into the heliosphere, trying to fit every single point in the sky. But they're not actual points, they're lines of sight integrations. So then you have to have a weighting function of the scattering along each line of sight, so the contribution to each part along the line of sight. And then you do that 9 times. You throw out the few sources that don't fit. Usually, typically, it's 1 or 2% of the sources get thrown out. Then you do it another 9 times, and eventually you settle down to a nice, settled heliosphere and a nice structure. And 80% of the time, it compares well with in situ. 20% of the time, it doesn't, but then that's most of the time because you've got, for example, during the peak of winter, STELab can't see below about minus 10 degrees on the sky. So anything in the southern hemisphere, we got no observations for. So anything in the reconstruction is just made up out of noise and inference. So you have to, make sure you don't pay attention to that. So a little bit of knowledge is needed. You can't just look at these and think, hey, wow, that's good. There must be something there. But at the same time, when you've got good data coverage, things really do work well, and the forecasting works pretty well as well. I think Jan was next. Sorry. Right. The tomography works best if you've got an initial 4-5 weeks of data, so an initial counter rotation of data. But as soon as you've got your counter rotation of data, every time you take observations, and they're updated on a daily basis at the moment. So the UCSD computers connect to STELab in Japan, updates every day, and it runs the tomography. But the tomography actually runs every hour. It just doesn't get any new data until every 24 hours. But what it's doing is it's now incorporating real-time ACE in situ data. I don't know if these are a little bit too small. I managed to get these through the night by setting my alarm for every 3 hours. And you can see that there's this structure here, which was responsible for yesterday's enhancement over Europe. And you can see then 3 hours later, you can see that this structure is slowly moving out, and again moving out and out again. But if we switch to look at what the in situ plots are telling us, well, here the forecast is saying that in a few hours' time it's going to slowly decrease again in density. And here it's saying that there's going to be a little bump in velocity and then it's going to carry on. And if you look 3 hours later, indeed the ACE data are starting to come down in density and down a little more and down a little more. So over that period of just 9 hours there, I mean, I should have done it for a longer period to show you better. I mean, it works around 1 to 3 days in advance, depending on what else is going on in the solar wind. But you can see there's been a pretty good job there of forecasting what is to come at the Earth. Jan, sorry.
If the VEC is a holy grail in far irradiation report, is it what would the LOFAR remove with the ionosphere?
That would be ideal, yes. In fact, Andy Breen, I don't know how many of you know Andy Breen, before he passed away a year and a half ago, he was actually involved in a sort of a pie in the sky project of thinking about designing a radio telescope to go on the far side of the moon. So it would be completely away from the Earth. There would be no terrestrial interference. Of course, you then have to work out how you communicate with it and so on and so forth. But that is what one of the ideas was. And then you can do a lot of solar observations for half of the time, and then a lot of astronomy observations the other half of the time, where it's on the side away from the sun and you can't use it for IPS, for example. Exactly, yeah. Hence the pie in the sky notion, where it's a good thought in principle, but in reality it would be very much of a technological challenge, to say the least. No? Okay, thank you again.